Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL Jan 2024 paper of Chemistry Unit 3. In question 1, we have to name these three functional groups. This is a group like this, two alkyl groups on its right. So this is a ketone. Functional group 2 is just a C11C, so this is an alkene. Functional group 3, this is a secondary alcohol. You don't always have to write the secondary before the alcohol, but it's always safer to do so in unit 3. Now we have to describe a chemical test and the expected positive result for both functional group 2 and functional group 3. So for functional group 2 was an alkene. So the test for alkene is to add bromine water or add bromine water. You can just write down bromine aqueous as well, and the result would be that it turned from orange to colorless or yellow to colorless. The result is yellow to colorless. Just decolorizes works as well. And functional group 3 was a secondary alcohol. Our test for secondary alcohol would be to add PCl5. The result would be as misty fumes or steamy fumes forming. The steamy fumes will form because when we react PCl5 with alcohol, we get HCl forming, which absorbs the moisture in the air, looking steamy. Now we have to find the m/z ratio of the fragment shown by the unshaded area. So we have 1, 2, 3. So CH over here, 1, 2, 3, 4. So a single carbon. CH2, CH2, okay. This has 1, 2, 3, 4. So this is a single carbon, and this is CH3. If we add it up, so we get 13 for this, 12 for this, 16 for this, 14 for this, 14 for this, 12 for this, and 15 for this. If we add that all up, 13 plus 12 plus 16 plus 14 plus 12 plus 12 plus 15. Adding this all up, we get 96. When in part 2 we are asked this question: when molecular ions fragment, they form a smaller ion and another type of a particle. We have to state the other type of particle. The other particle would be a free radical. So when the molecular ions, the whole ion fragments, one of them will be an ion, the other will be a radical. Have to remember that. Now in question 2, we are given this experiment carried out to determine the concentration of citric acid in a lemon juice using titration. We are given the steps. We add 24 grams of lemon juice to 250 cm3 volumetric flask. We prepare 25 cm3 of that to a conical flask and add a few drops of phenolphthalein. Then we titrate the dilute lemon juice with standardized sodium hydroxide of concentration 0.103 mole per dm cube. The concordant results would be this. Now we have to find the mean titer. So from the concordant results we have 2.30 plus 24.20, 24.30 plus 24.20 divided by 2, we get 24.25 cm cube. Now we are given this reaction, we have to state the color change that occurs at the end point. The phenolphthalein indicator was added to dilute lemon juice which contains citric acid. So the phenolphthalein was in the conical flask which was in acidic conditions. So the phenolphthalein was colorless at first. Then we added this sodium hydroxide which is an alkali. So the titration would go from acidic to alkaline. So for phenolphthalein it would be colorless to pale pink. Now we have to calculate the percentage by mass of citric acid in the lemon juice. So our titer was 24.25 cm cube. And so the number of moles of sodium hydroxide was its concentration, which was 0.103 times its volume, 24.25. We have to convert the volume into dm cubes, multiply 10 to the power minus 3. If we calculate this, we'll get a value of 2.49775 times 10 to the power minus 3 mole. So now the mole ratio of sodium hydroxide to citric acid is 3:1. So the number of moles of citric acid would be 1/3 of this. So this value divided by 3, 49775 into 10 to the power minus 3 divided by 3 moles. This is in 25 cm cube. So in 250 cm cube, number of moles of citric acid in 250 cm cube times 10 . Now we have to find the percentage by mass of citric acid. The mass of the lemon juice was 24 grams. Now we have to find the mass of citric acid in it. The mass of citric acid in the lemon juice was 2.49775 times 10 to the power minus 2. So if we multiply this with this, if you don't want to change it, we can keep that as well. So this is the number of mole, and the molar mass is 192. We get a value of 1.5986 grams. So the percentage by mass, 1.5986 divided by 24.0 times 100, we get a value of 6.66% We were asked to give it in 2 SF, so 6.7%. Now moving on to the next part, we have to suggest a possible reason why the value obtained in C is valid, even though lemon juice also contains some ascorbic acid and malic acid. If we have other acids, they would also affect the titer value. So the sodium hydroxide that we used in part C would also be used to neutralize the ascorbic and malic acids. However, we have to suggest a possible reason why this answer might be valid. This might be due to the amount of ascorbic acid and malic acid in the lemon juice being in such low quantities that our titers isn't affected that much. So the other acids. Now moving on to part E, we are given that 2 other students B and C also followed the procedure to find the concentration of citric acid in similar samples of lemon juice. Student B added too much deionized water in step 2. We have to state how the student should correct this mistake. We can restart our experiment over here, or we can transfer it to a larger volumetric flask and then do the experiment over there. So the second one has less hassle and waste, so I'll write about that. However, this option might not be available at all times, so we might have to restart our experiment as well. Transfer the lemon juice. And then we have to make up to volume in the larger flask. And now we are told that student C used sodium hydroxide solution labeled 0.103 mole per dm cube that had been made up several months ago and stored since then. We have to explain what this effect would have on the mean titer. If the solution was made months ago, some of the water would have evaporated, so the mean titer would be less than what student A would have found. Since there is less water now, the sodium hydroxide is more concentrated, so the mean titer would be less. So a smaller volume of sodium hydroxide would be needed. Now moving to question 3. We have this experiment where seaweeds. We have this experiment is about obtaining iodine from the ash produced by heating seaweed. In step 1, we are told that they heat the dried seaweed strongly to burn off any organic material. We have to suggest in part A why the iodine containing compounds do not burn off. The iodine containing compounds are ionically bonded, so they have a high boiling and melting temperature. So you can just say that the iodine containing compounds are ionically bonded. Causing them to have high melting and boiling temperatures. So in the experiment, we add the ash produced in step 1 to 25 cm³ of deionized water and then boil for 5 minutes. We filter off the remaining solid, then add 2 cm³ of dilute sulfuric acid followed by 10 cm³ of 20 volume, which has hydrogen peroxide solution. Then we extract the iodine formed in step 4 using cyclohexane as the solvent. So we use solvent extraction over here, and then we allow the cyclohexane to evaporate and leave behind the iodine crystals. Now in part B, we are told that 20 volume hydrogen peroxide solution means that 1 dm³ of the solution produces 20 dm³ of oxygen gas when it decomposes completely. We have to calculate the concentration of 20 volume hydrogen peroxide solution. So the volume of oxygen produced would be 20. We'd have to use the ideal gas equation, PV equals to nRT. Okay, no, we don't have the pressure. We can calculate the moles of oxygen produced. So 20 dm³, the molar volume of gas would be 24, so 10 by 12 or 0.833 moles of oxygen. So the number of moles of hydrogen peroxide would be twice of that, since the mole ratio is 1:2. So 2 into 0.833. Since the volume is 1 dm³, this is the concentration itself. So the concentration is this divided by 1. So we get 1.67 mole per dm³. Now in question C, we are told that in step 4, the iodide ions in the filtrate are oxidized to form iodine. The reaction takes place under acidic conditions and the hydrogen peroxide is reduced to form a single product, water. We have to write half equations for this. So the oxidation of iodide ions would go from iodine. So we form iodine from iodide ions. To balance the charge, we'll add 2 electrons on the right and the reduction of hydrogen peroxide in acidic condition forms water. So hydrogen peroxide on this side, water on this side. The oxygen don't balance out. We have 2 oxygens on the left and 1 on the right, so we can add a 2 over here. However, now the hydrogen is not balanced. We have 2 hydrogen on the left and 4 on the right, so we add 2 more H plus on the right. Now if we want to balance the charge, we have 0 on the right plus 2 on the left, so we add 2 electrons on the left. Now we have to write the overall equation, so we can just add these 2 up because both of them had 2 electrons. So we'll get H2O2 plus 2H plus 2I minus, and we'll get iodine plus 2 moles of water. Now we have to state the color of the aqueous iodine solution. Iodine solution usually have a brown color. Now we have to describe how to carry out step 5 using a separating funnel. Step 5 was solvent extraction. So we have to describe how solvent extraction takes place. Basically describing the solvent extraction, we are given the density of cyclohexane, which is 0.78 gram per cm cube. It's a 4-mark question. So we put the filtrate in a separating funnel, which looks something like this. You have a tap in the end. You have a tab that you can control. Also put a cork at the top to seal it out, a cork or a stopper. You put your cyclohexane over here and the iodine solution. So we add the iodine solution to the cyclohexane. The density of the iodine solution would be 1, so this would be the iodine solution. It's more dense, so it's gonna be at the bottom. So this will be the cyclohexane layer. This will be the aqueous layer. Since iodine is a non-polar compound, it's gonna dissolve more in the cyclohexane layer. So the iodine is gonna be in the cyclohexane layer more. And it will be in very low concentrations in the aqueous layer. Now after we add the iodine over here, we'll invert this upside down a few times. We're gonna shake it to mix it up. We are also gonna invert it, so flip it upside down. And while it's upside down, we are gonna open this tap over here a few times so that the gas pressure is released, so that we don't have an explosion inside the tube over here. Then when the layers separate, we'll just open the tap and pour one of the layers into a beaker and keep the other layer in here. So if we write our answer, we would first add the iodine solution, to a separating funnel containing cyclohexane, and then we gently shake or invert. Invert is more used, so inversion is a better technique than shaking. Now we write about the tap, so we can write periodically or occasionally opening the tap. Then we'll allow the layers to settle, so we keep the separating funnel at the same position for a while, allowing the layers to separate. After inversion, the layers will be mixed for a while, so we'll have to let it sit for a while. Since we are given this detail about the density, we have to show that we know that the aqueous layer is gonna be in the bottoms. So we have to show them that we know that the density of water is 1 gram per cm cube and it's gonna be in the lower layer because it's denser. So that's how we construct our answer for this. Now moving on to part E, we have to state what is meant by symbol 3. This is the symbol of a serious health hazard. This is a health hazard. This is the symbol for flammable stuff. It's better to write serious health hazard over here. This is for flammable objects. This is for health hazard. And this is for serious health hazard. This symbol is also used for danger to the ozone layer, but it's less relevant nowadays. Now we have to give 2 safety precautions that could be taken to reduce the risk in step 5, assuming we have eye protection gloves and laboratory coats. Since dangerous fumes are being produced, we should carry it out in a fume hood. Carry out the reaction in a fume hood. And we should avoid contact with the flames as well, since we are flammable objects over here. Cyclohexane is a flammable object over here, so we should not carry it out near flames. Don't put near sources of ignition or flames. Now moving to question 4. In part A we are given this data over here. We have to calculate the density of an ethanol water mixture, sample A, 5 cm cube, of which have a mass of 4.75 grams. So if we find the density in gram per cm cube, we'll have 4.75 divided by 5. We'll get 0.950 gram per cm cube. Okay. Now moving on, we have this graph to plot. The smallest value of the percentage is 30 while the largest is 95, so we'll take 30 to 100. So the smallest value is 30, the largest is 100. So we have 1, 2, 3, 4, 5, 6, 7, 8 boxes. So 100 minus 30 by 8. So if we take 10 on each box, we'll get a good enough coverage. 60, 70, 80, 90, 100. So we are using most of our x-axis with this scale. Now for the y-axis, the smallest value is 0.811, the largest is 0.962. So we can take values from 0.8 to 0.97. 0.97 minus 0.8, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. So around 0.02 per box, starting from 0.8, 0.8284, 0.86, 0.88, 0.90, 0.92, 4, 0.96 and 0.98. Our first pair of value is 30, 0.962, 30 over here and 962, so it's over here. 10 boxes are represent 0.02. 10 small boxes represent that, so each small box represents 0.002. So 0.962 is over here. Now the next pair of points is 45, 0.940. 45 is over here in between 40 and 50, and 0.94 is over here. So this was 40, this is 50. The next pair of points is 55, 0.92. So 55 is over here in between 50 and 60, and 0.92 is over here. Now we have 70, 0.886, 70 over here, 0.88 over here. So we have 0.882, 884 and 886. Now for the next pair we have 0.85 comma 0.845, 85 over here, 0.84 over here, 842 is over here, 844 is over here, 845 is in between this. Now for the last pair of values we have 95 comma 0.811, 95 over here, and 0.81 is over here, 811 is over here. Now we'll just draw a curve to connect all those points over here. My line is pretty shaky and inaccurate. You can draw it much better than I am doing. Now we have to determine the percentage of ethanol by volume using our answer to part A1 and the graph in A2. Our answer to A1 was 0.95 grams. So we have to find the percentage of ethanol by volume when the concentration is 0.95. So for your graph, you'll go for the value corresponding to 0.95 and find the x-axis value for that. My graph isn't too accurate over here, so your values might differ. For my graph I get a value of 39. The mark scheme answer is 38.5%. So my inaccurate graph was pretty accurate. Now in part B we have ethanol, which can be prepared by heating ethanol with acidified sodium dichromate in this apparatus. In this question we have to explain why the reaction mixture is heated in this setup over here instead of heating under reflux. So in this case we use distillation to remove aldehyde. This aldehyde over here, the ethanol, we use the distillation to remove this. If we were heating under reflux, the ethanol would return to the reaction mixture, which might have resulted in the formation of ethanoic acid, which we don't need in this case. So the distillation allows us to remove the product. As it is formed, which prevents the formation of ethanoic acid. Now to the next question, we have to explain why the water is passed through the condenser in the direction shown. So we have to explain why the water is going into the condenser from down here, then moving up and out through the top. If the water is moving in from the bottom, it fills the whole condenser. If the water was just going in, it would directly go out. If the water is going up, it will fill everything up and then go down and out of the condenser. So our answer is let's water fill the condenser, which results in more efficient cooling. Now in question 4C, we are given that a student who determined the value of the enthalpy change of combustion of ethanol using the apparatus below. We are given a spirit burner containing ethanol and 100 cm cube of water in a copper calorimeter. We are measuring the heat energy gained by the water to find the enthalpy of combustion of ethanol. So we need to find the energy transfer to the water at first. The mass of water would be 100 grams. The specific heat capacity is 4.18 joules per gram per degree Celsius, and the temperature change is 57.9 minus 20. So the energy transferred would be 100 times 4.18 times 57.9 minus 20. So 15,842.2 joules. Now we have to calculate the amount of ethanol burnt in moles. So the amount of ethanol burnt was 0.650 gram. The number of moles is the weight divided by the molar mass, which is 46.0 gram per mole. 65 by 46. We get 0.01413 moles. Now in part C3, we have to use our answers to C1 and C2 to find the enthalpy change of combustion in kilojoule per mole. So del H would be Q by N. The energy transferred this is in joules. We have to convert this into kilojoules before we put it over here. So we multiply 10 to the power minus 3, and in the denominator we have 0.01413. We get a value of 11,020. 11,020 kilojoule per mole. This is an exothermic reaction, so we put a negative in front of it. Now in this question we are given this detail as well, so we have to give our answer to appropriate number of significant figures. Appropriate number of significant figures is using the number of significant figures in the data value with the lowest number of significant figures. In this case, all of the data is given in 3SF. So every value we see over here is given in 3 significant figures. So our answer should also be in 3 significant figures, which we have done. Now to part D, we are given this apparatus over here. So this is an alternative apparatus to the reaction in part C, which was this over here. So We were increasing the temperature of water and measuring that change to find the energy that was produced by the burning of ethanol. So now we have to give two reasons why this apparatus over here is more likely to give an accurate value for the enthalpy of combustion. Now what's different with this is, instead of having a different beaker, we have this copper coil running through. The copper coil running through the water heats the water up. So basically the spirit burner and ethanol heats this up. The heat goes through the copper coil. The copper coil is submerged in the water, which causes the water to heat up. The copper coil is a better conductor of heat than air, so this reduces the heat loss. This is one of the point. And also we have this oxygen air mixture which is going into this spirit burner over here. This mixture, this air with oxygen, will cause the apparatus to have a higher supply of oxygen, which would result in them giving a higher rate of complete combustion. So constant supply of air into the apparatus causes the chance of incomplete combustion to decrease. And that's it for this paper.